Math 2414, improper integrals. Infinite limits of integration, example 1. The next 1, 2, 3, 4 videos, 5 videos, are all just examples of doing improper integrals with infinite limits of integration. So let's take a look at this first one. And you might recognize this one as an integral that I introduced in the very first video. The integral from 1 to infinity of 1 over x squared dx. I do need to introduce a little terminology though. When you're looking at an improper integral, there's actually 2 questions you can answer. Number 1, does the integral converge or diverge? And number 2, if it converges, find its value. So what does it mean for it to converge or diverge? Well, in the context of limits, when we say the improper integral converges, we basically say that the limit exists, the limit that we set up. And to say that it diverges means the limit does not exist. Now, as one person in my class has already asked me, there is a much more technical definition of what it means to converge and diverge, involving something called deltas and epsilons. When the time is right, we'll talk about those when we get to the chapter about infinite series. But for now, let's just say that converges means the limit exists and diverges means the limit does not exist. And if you're starting to have nightmarish flashbacks to Calculus 1 about proving a limit using deltas and epsilons, it's kind of like that, but way more. All right, let's take a look at this one. The integral from 1 to infinity of 1 over x squared dx. We have a strategy for doing this. And remember, the general strategy for attacking an improper integral is to replace the problem with a variable, do the integral that way, and then take a limit. So first, we need to evaluate the integral from 1 to t of 1 over x squared dx. Well, this is pretty standard. This is just a calculus 1 integral. If you integrate 1 over a power, just write it as a negative power. So we're going to integrate x to the negative 2 from 1 to t. Well, power rule says add 1 to the exponent, which is negative 2 plus 1 is negative 1, and then multiply by the reciprocal of that, and we're evaluating this from 1 to t. Let's clean up the antiderivative. It's going to be a fraction, it's going to be negative, and the denominator is just going to be x, and that's going to be evaluated from 1 to t. All right, we substitute t, we get 1 over t, minus, if we substitute 1, we get negative 1 over 1. Well, negative 1 over 1 is just negative 1, and we're subtracting it, so it becomes a plus. And so our antiderivative is negative 1 over t plus 1. But that's not the answer to our integral. That's simply the answer to the definite integral if we replace the problem, the infinity, with a variable. Second, we take the limit as t approaches infinity of that antiderivative. Negative 1 over t plus 1. Well, this is pretty easy. You don't even need the rules we talked about in the previous video to do this. Just use some common sense. The t is living underneath a 1, and the t is going to infinity. I have a fraction whose numerator is static and whose denominator is exploding. And in a fraction, when the denominator gets larger and the numerator just sits there, the fraction collapses down to 0. In other words, this limit is 0, and so we get 0 plus 1, which is equal to 1. And that would be the value. So if we wanted to answer our question, therefore, we could say the integral from 1 to infinity of 1 over x squared dx converges to 1. That would be a good way to wrap that up. Geometrically, this means if we took the graph of 1 over x squared, and I'm only in quadrant 1 because I'm going from 1 to infinity, what we're claiming, and it would be the correct claim, is the area under this graph from 1 to infinity is actually just 1. Well, that wasn't too bad. But I can hear my students now. Yeah, but what about the ones in the homework? Yeah, I know it's gonna get uglier, not just in the homework, but in these videos, but they're not all that bad. This one wasn't that bad at all.